The ideal gas equation. We can use apparatus like this to investigate how the pressure of a fixed mass and volume of gas is affected by its temperature. We have a sealed flask onto which is placed a pressure gauge with very little change of volume, and we have the flask in a water bath which we can change the temperature of, measuring with a thermometer. If we plot a graph of pressure against the temperature in Kelvin, we get a straight line through the origin. This shows us that the pressure is directly proportional to the Kelvin temperature. Just to stress again, the temperature must be in Kelvin. We can use apparatus like this to investigate the relationship between volume and pressure of a fixed mass of gas at a constant temperature. Here, air from a pump fills the top of this vessel, pushing oil along here and compressing a fixed mass of gas in this tube. We can measure the volume of the gas using this scale, and the pressure from this pressure gauge will be the same as the pressure here. If we plot a graph of pressure against 1 over volume, we get a straight line through the origin. This shows us that pressure is directly proportional to 1 over volume, or pressure is inversely proportional to volume. So the first experiment showed us that pressure is directly proportional to temperature for a fixed mass of gas at a constant volume. The second experiment showed us that pressure is inversely proportional to volume for a fixed mass of gas at a constant temperature. We can combine these to say that pressure times volume is directly proportional to temperature. Or we can change this to an equation by adding a constant. In this case, the constant is N times R. Let's define the terms. P is the pressure in pascals, V the volume in cubic meters, N is the number of moles of gas in moles. R is what is called the molar gas constant and has a value of 8.3 joules per mole per Kelvin. And T is the temperature, which must be taken in Kelvin. This is known as the ideal gas equation. An ideal gas is a simplification which assumes there are no forces between the molecules except during perfectly elastic collisions. The internal energy of the gas is entirely kinetic and depends only on its temperature. Real gases behave very much like ideal gases as long as the pressure is low and they're at a temperature well above their boiling point. We can rearrange the ideal gas equation to get all the variables on one side and constants for a fixed mass on the other side. So this right-hand side now will be a constant value. So if we have a fixed mass of gas, we can say that the pressure times the volume over the temperature in one circumstance will be equal to the pressure times the volume divided by the temperature in a second circumstance. Let's look at an example. A sealed container of gas at a temperature of 20 degrees Celsius and atmospheric pressure at 100,000 pascals has a volume of 0.6 cubic meters. How many moles of gas are in the container? Well, for this we need to use the ideal gas equation, and we can rearrange for the number of moles as pressure times volume over the molar gas constant times the Kelvin temperature. Putting in the figures we know, we've got the pressure at 100,000 pascals, the volume 0.6 cubic meters, the molar gas constant 8.3 joules per mole per Kelvin, and 20 degrees Celsius is 293 Kelvin. We can then put in the values given, and we get an answer of 25 moles. The container is now heated to 200 degrees Celsius and expands to 0.8 cubic meters. What will the new pressure be? Well, for this we need pressure 2 given volume 2 and temperature 2. And from this example we can take pressure 1, volume 1 and temperature 1. So we can use this expression Rearranging for pressure 2, putting in the values, we had 100,000 pascals times a volume 1 of 0.6 cubic meters. The second temperature is 200 degrees Celsius or 473 Kelvin, divided by temperature 1 of 293 Kelvin and the second volume of 0.8 cubic meters. This gives a new pressure of 121,075 pascals.